Hello, gals and guys. Mr. Ambrose here with a video on what you missed, unfortunately, in class today due to the tech issues that I had with my Chromebook. So we continued working just with improper integrals in class today. But just a reminder, yesterday, right, we started looking at improper integrals, and we said that this improper integral here, the first one we looked at, because of what we saw when we did all our work, we saw that improper integral diverged because the area underneath the curve and between the curve and the x-axis from 1 out to infinity was infinite. And then from there, right, we started working on this problem here where we pretty much had a graph that looked very similar to the graph of y equals to 1 over x. And we were trying to determine, was this also going to have an infinite amount of area? And as we did with the first improper integral, right, we said that, okay, we can set up this Mr. Smiley face to the right of x equals to 1 so that we can write this definite integral with the same integrand. And the idea was that to equate this ultimately to the improper integral, we would want to send Mr. Smiley Face off to infinity, right? And so this is where we left off from class yesterday, and this is where I picked up with those in class today, or those in live instruction today. All right, so to help evaluate this whole kit and caboodle expression, I'll perhaps just try to evaluate this definite integral, and I'll do so on the next screen. So, right, I want to evaluate right, this particular definite integral. And to do that, right, we need to determine what is the antiderivative of 1 over x squared, right, which we can essentially just rewrite the fraction as a power, x to the negative second power in particular. And then the antiderivative of that would be x to negative 1 divided by negative 1, technically plus some constant. If you happen to forget the plus c when evaluating a definite integral, that's fine. But to help evaluate this definite integral, I'd like to rewrite it without the negative exponent. And so negative 1 over x is essentially our antiderivative. So using that antiderivative, I can now evaluate this definite integral. And so we plug in the upper limit first, right, when evaluating our definite integral. And then we subtract from that what we get when we plug in the lower limit into our antiderivative. And essentially, the value of this definite integral becomes negative 1 over Mr. Smiley Face minus negative 1 over 1, which is really just becomes plus 1. And so the value of this definite integral here, I'll now plug into our expression here. And I'll just carry forward the limit. And again, the value of our definite integral was negative 1 over Mr. Smiley Face plus 1. And now the last thing to do is to try to evaluate this limit. And as Mr. Smiley Face goes off to infinity, right, that's going to make the denominator of this fraction immensely large. And so this fraction is going to approach 0. And that means the value of this limit, where this limit is going to approach, will be 1. And so since the limit in this example exists, it actually equals 1, we can say that our original improper integral, right, when we get this finite value, when we do this evaluation, we can say that this improper integral converges, and in particular, we can say converges to 1, right, because the area in this region bounded by the graph, the x-axis from 1 all the way out to infinity, the region technically goes on forever, but technically as we continue to add and add more area in this region, it's not going to blow up, and as we continue to incrementally add more area, it's going to ultimately approach the value of 1. And that's why we say when this improper integral has a finite value, we say it converges to that particular value. All right. So now that you've seen this here and the improper integral from yesterday and how we evaluated it, now I'm just going to define our improper integral and how in particular we go about trying to evaluate it, right? So if we have any particular improper integral where a is a constant, we always will want to replace the infinity or where we have some sort of value making the improper integral improper, we're going to replace that with our variable, and it could be any variable. It doesn't have to be Mr. Smiley Face. It can be any variable you like. And then we put this limit out in front. And so once we have that improper integral, rewritten as such with a limit, if that limit of that def integral exists, then we will say that the improper integral converges. But if the limit of that improper integral does not exist for whatever reason, then we say that that improper integral diverges. And this is a definition that we have for our improper integral. And essentially, it also kind of tells us exactly how to go about evaluating any improper integral, which is, again, replace this infinity or whatever value you need to with a variable, put a limit out in front, and then try to evaluate this whole kit and caboodle expression to see what the end result of your improper integral will be. All right, so then from here, what we did in class was we just looked at a couple examples to just practice evaluating these improper integrals. So instructions that tell us to help us realize that we're dealing with an improper integral will be something along the line of this here, where you'll notice it says here to determine if the following converge, and we're looking at an integral. So I see the negative infinity in here. That further confirms to me that this is an improper integral. And so the first step I'm going to do is that negative infinity, that's really making this integral improper. I'm going to replace that with my variable, Mr. Smiley Face. The rest of my integral will remain the same, but I also need to put a limit out in front of our integral, this def integral now. And now this is going to be a limit as our Mr. Smiley Face approaches this negative infinity expression. All right, so now we have to determine essentially if this whole limit exists, the limit of this def integral exists. And so to do that, I'll off to the side go and evaluate my definite integral expression using the fundamental theorem of calculus. And so, right, the antiderivative of e to the x we know is simply just e to the x. And then I'll plug in the upper limit of integration first into our antiderivative, and then the lower limit second into our antiderivative. And e to the 0 we know is equal to 1, so I'm just going to simplify that. And I have here now an expression for the value of our definite integral. And so I'll go back to my original improper integral and my equality here, and I'll carry forward my limit expression. And then I will substitute in for this def integral the value of that def integral, which is 1 minus e to the Mr. Smiley Face. And so now we have to try to evaluate this particular limit. And there's two ways perhaps to try to consider exactly what in particular is happening to e to the Mr. Smiley Face as Mr. Smiley Face raises off to negative infinity. One way to try to evaluate that would be to consider the graph of e to the x, or to consider what that looks like, and use that to try to piece together exactly what's happening as x in particular raises off to negative infinity. And x approaches negative infinity, we go out to the left in our coordinate plane to have x approach negative infinity. And on our exponential function graph, e to the x, right, that exponential function graph is going to approach the x-axis and thus approach 0. So that would be exactly what e to the Mr. Smiley Face will approach as Mr. Smiley Face approaches negative infinity. So the value of this overall limit then ends up being 1. And since that means that this limit, since it has a finite value, the limit exists, that means that we can say that the original improper integral here converges, and in particular we can say it converges to the value of 1. All right, so the second and last problem that we did in class today was this one here, which the instructions are still the same. We're going to try and determine if this converges or not. But when you look at this integral, you may say, well, it doesn't look like it's improper because I don't see one of the limits of integration be infinity. Well, although that may be the case, there's something happening with one of these limits of integration and our integrand. And in particular, one of these limits of integration, when we plug it into the integrand, is going to cause that integrand to be undefined. And hopefully we would agree that at 0, when we plug that into this integrand, right, that's going to make that undefined. And that's where we're having an issue. That's where this def integral, or what looks like this def integral, where that makes this an improper integral. So the other thing to consider, and technically you don't have to worry about this when you ultimately evaluate this improper integral, but if we were to actually look at this graphically, the graph of 1 over the square root of x looks very similar to our graphs of y equals to 1 over x and the graph of y equals to 1 over x squared, right? This graph of y equals to 1 over the square root of x looks very similar to those. And if we then consider the region that is in between this graph and the x-axis from x equals to 0 to x equals to 1, we can sort of see now, especially why this is going to be improper, because of the potential that this area in this bounded region, well, it may blow up and go to infinity, or it may, could it perhaps actually have a finite value? Could this actually approach a finite number? Right, this is definitely an improper integral, and now we will evaluate it in the same manner as we did all the other prior improper integrals. So the idea again is that we can place our variable, Mr. Smiley Face, on the given interval, and I'm going to rewrite our integral with the same integrand. 1 is going to remain in there, but because 0 is where we have the issue that's making this integral improper, I'm going to replace that with my variable, Mr. Smiley Face. I'm going to put my limit notation out in front of the improper integral, or I'm sorry, now in front of the def integral. And since Mr. Smiley Face is going to be located somewhere here in the interval between 0 and 1, we're going to want Mr. Smiley Face to approach 0, and Mr. Smiley Face is going to approach 0 from the right-hand side. So I'll write here, Mr. Smiley Face is going to approach 0 from the right-hand side. And now I have basically my improper integral rewritten in the proper form with a definite integral inside a limit. And what I'll now do is I will go about trying to first evaluate just this definite integral. And obviously to do that, I'm going to need to know what is the antiderivative of 1 over the square root of x, which that can be rewritten as x to the negative 1/2 power. And the antiderivative of x to the negative 1/2 power is x to the 1/2 power divided by 1/2 plus some constant, which this will simplify down to 2 times the square root of x plus some constant c. If you happen to forget to write the plus c there, in this particular example, ultimately we're using this to help evaluate our definite integral. So if you do forget to write the plus c there, no biggie, you won't lose credit. But now I'm going to use this particular antiderivative to help evaluate our definite integral. So we plug 1 first into our antiderivative. So we'll have 2 square root of 1. And then we'll subtract from that 2 square root of Mr. Smiley Face. And so now, since this here is our value to our definite integral, I'll use that to help us ultimately evaluate that particular limit expression. So I'll bring down this limit as Mr. Smiley Face is going to approach 0 from the right. And I'll plug in the value of this def integral, which is essentially this equals 2 minus 2 square root of Mr. Smiley Face. And so now when we go to evaluate this particular limit, as Mr. Smiley Face approaches 0 from the right-hand side, hopefully we agree that that would essentially just be equal to 2. And since, once again, the limit exists here, we can say that this improper integral converges, and in particular, we can say it converges to 2, right? Meaning, thus, this area, although this region technically continues to go on forever because this graph will never touch the y-axis, although this region continues to go on forever, as we continue to add more and more area to what we currently have, right? Incrementally, as we add more and more area, that area's total value is going to ultimately approach and get closer to the value of 2. All right. So that was pretty much it, and what we covered in class today. Again, I apologize for the technical issues, and hopefully tomorrow that won't be the case, and it hopefully won't be the case. Again, in the year, I have my concerns that it perhaps may happen here and there, but hopefully, again, it won't happen that frequently, and hopefully not at all. To practice evaluating these improper integrals, please try to do question numbers 8 and 18. You're not responsible for submitting them because, again, of the tech issues that we had today, but try them out. My solutions are posted, and tomorrow, before we move on to the next topic, I'll go over any questions you may have had on these particular problems. All right. Again, I hope this video helped you guys out, and I hope you guys have a great night. Take care, everyone.